And we're back looking at vectored valued functions, 10.3b. So now we're looking at derivatives of vectored valued functions and integrals of vectored valued functions. Yeah, I got lazy and started abbreviating vector valued functions, VVF. I wouldn't do that on the AP exam, guys. All right, so derivatives of vectored valued functions. Much easier than parametric. So parametric, we're putting all this stuff together. Vectored value functions, we're keeping things separate as vectors. So that means if we want to take derivative of, say, our vector function r of t, the first derivative would just be the derivative of each part separate, still as a vector. The second derivative, again, the derivative of the first derivative. So we just keep taking derivatives of each part separately, and that keeps giving us our derivatives. All right, so real basic derivatives, we're just doing a derivative of each part. All right, so vectors are often used in physics for position, velocity, and acceleration. So if we look at this guy, for t greater than or equal to 0, the position of a particle is given by s of t, so this is a vector valued function, is cosine of t times I plus sine of t times j. So this is our x of t, and sine of t is our y of t. All right, so first off, what's the position at t equals pi over 3? Well, if we want the position, we just plug into the original function. So we want s of pi over 3. So that would be cosine of pi over 3 times I plus sine of pi over 3 times I, or sorry, times j. I gotta turn my eyes around. J, there we go. All right, so we can just look at pi over 3 is a 60-degree angle. So 30 degrees here, so that's 1, 2, square root of 3. So we get that it is cosine of that is 1 over 2. So we get 1/2 I plus sine of this is root 3 over 2. So we get root 3 over 2j, like that. I keep putting my j's backwards. I'm not used to writing lowercase j's. So we can write it like that. We could also write it in our bracket notation, 1/2 comma root 3 over 2. All right, the AP exam seems to use this more from what I've seen, but physics will use this more. So if you're in physics, you're probably using I and J notation already. All right, if you're curious, so that was just the position at this point. We could get the actual graph of that. And the way we would get the graph is the same way we would do it using parametrics. We'd use cosine squared plus sine squared is 1. So it would just be x squared plus y squared equals 1 would be the graph. So it's a circle with radius 1. That's going to start at, if I plug in 0, I get cosine is 1. If I plug in 0, I get sine is 0. So I would start right here, and it's going to go around, I believe, like that. So it does have a direction as it goes, just like the parametrics had direction. But it's just going to be a circle. So this is s of t, our vectored value function. All right, and we just found that we're at pi over 3, we're at 1/2 and root 3 over 2, so we're probably up there. It's going to go away. There it is. So there's our point, 1/2 root 3 over 2. In other words, it's a vector coming out from the axis pointing to that point. I kind of missed it there, didn't I? Let's try again. There we go. There's our vector. All right, what's the velocity at that same time? All right, well, to find the velocity, we just take the derivative. So we need, so our velocity function, v of t, will be s prime of t. So derivative of cosine is negative sine. I'm going to go ahead and write it with bracket notation. Negative sine of t, and the derivative of sine is cosine of t. So there's our derivative. So now we're just going to plug in pi over 3 here. All right, I've already got the triangle drawn. So sine is root 3 over 2, and we've got a negative sign, so it's negative root 3 over 2. And our cosine value at that is just going to be 1/2. Now the question is, how does that relate to this? So it looks like my slope would be like something like this right here. But this vector says I'm going negative root 3 over 2 and then down 1/2. It looks like I'm going pointing from here towards there is what the vector is saying. Oops, sorry, going up. So back and then up like that. Well, if I just take this and just kind of slide it over here, it's going to say the same parallel vector right there. So I'm just moving this vector up to here, and it's saying, oh, it's going like that. So this is how vectors are very useful in physics, and maybe in Calc 3 when you do this a little bit more. Like they tell you exactly at the point which direction you're going. So from this point, I would be going back negative root 3 over 2 and then up a half. And that's exactly the direction it's going. So it does work just like slope. If you want to make a slope, you could just divide between the two. But we leave it as a vector because we are working with vectors. So that is our velocity at that point. So this is v at pi over 3. Find the acceleration. So how fast is it going in that direction? All right, well, we need one more derivative because remember the acceleration would be the third derivative. So this is position, s of t, this is velocity, v of t, and this is acceleration, a of t. So the third derivative, a of t, would be s double prime of t. And remember on the AP exam, don't just switch to a and v. Actually write like what it is in terms of the original function. So the derivative of negative sine is going to be negative cosine of t. Derivative of cosine is negative sine of t. Oops. So used to writing parentheses. There we go. And now we're going to plug in pi over 3. So we get that the acceleration at pi over 3 is cosine is 1/2 and it's negative. So we get negative 1/2. Sine is also negative here and it's root 3 over 2. All right, and that just tells us how fast it's moving, or how fast its rate of change is changing. All right, so that is just basic derivatives with vectors and position, velocity, acceleration, how that all works. We'll come back to more of that later. All right, with integrals, all right, it works just like derivatives. So if we have some sort of vectored valued function r, that's x of t and y of t inside a vector, and we want to integrate r, we integrate each part separately. All right, so now these are indefinite integrals. They don't have numbers on them. So that means that each one is going to get a plus c. So these plus c's can be different. So usually we say this is plus c1, and this one ends up plus c2. And if we have a point, or another vector, I guess I should say, we can use that other vector to solve for c1 and c2, just like we would normally do with a point. All right, if we have a definite integral, then we don't have to worry about the plus c's. We just take the definite integral of each part separately. We keep the comma in between. We keep the brackets. We keep it as a vector. Or we keep our i's and j's if we want. All right, so here's an example. R prime of t is this one function here and this other function here. So this is our x of t and this is our y of t. So x of t is t squared plus e to the negative 2t. Y of t is 1 over t squared plus 1. Find the integral of r prime of t dt if r of 0 equals 2I minus j. This is our point right here. This is what we think of as our point usually, but in this case it's a vector. And that means when t equals 0, we get x of t, x of 0 in other words, is 2, and y of 0 is this negative 1 right here in front of the j. So we're going to use that to find our points. All right, so now if we want to do the integral of r, we just do the integral of each part separately. So we're going to have inside the vector the integral of t squared plus e to the negative 2t dt, comma, the integral of 1 over t squared plus 1 dt. All right, to integrate this one, I'm just going to do each part separately. The integral of t squared is t cubed over 3. This one would be a little u substitution. We'd have u equals negative 2t, du equals negative 2 dt. So we'd put in a negative 2, we'd get a negative 1/2 out front. And then we get e to the u, but u is negative 2t. And that's going to be plus some c. This is still inside the vector. This guy, 1 over t squared plus 1. Bells and whistles should be going off in your head. This is exactly the formula for the arctan of t. And again, plus some other c, c2 say. So now, if we plug in 0 for this guy, for t, we should get 2. So we get 0 cubed over 3 minus 1/2 e to the 0, which is just 1, plus c. 1 is going to be equal to 2, so this is 0. Add the 1/2, we get c1 is 2.5 if you want, or you can say 5/2. So we get t cubed over 3 minus 1/2 e to the negative 2t plus 2.5 for the first guy. For the second one, we're going to plug in 0. We should get negative 1. So we get arctan of 0 plus C2 equals negative 1. Arctan of 0 is just 0, so we get that C2 equals negative 1. So we'd write arctan of t minus 1 for our other vector over there, and now we've integrated. So we just did each one separately. It's just like two little problems within one. All right, and that's how we do derivatives and integrals. So now in the next video, we'll come back and we'll do some more applications with position, velocity, acceleration, distance traveled, displacement, all that sort of stuff.